Hi there, everyone. It's Tim here, trying to do, I guess, episode 23. So let's go to our episode program, hit 23, and I guess what I want to do for this episode is basically pretty much continue on the maze generation. So I'm not sure what to put here, actually. I guess I guess I could put maybe I should put a maze generation part 2 or something. So we did make a lot of positive progress on this so far, and that's exciting. I mean, we didn't get close to finishing yet, but we did actually make positive and definite progress. So, I mean, I'm not sure if I can take a picture while recording. I guess I can. Well, anyway, that's that. So let's go back to our maze program and see what we can do. I'm kind of curious what comes next and how close we are to actually finishing this thing, because I'm kind of excited to see if we can actually get a complete maze created. So the last thing we made was the removal of the lists. So to check to see if walls are actually connected already or not. And then we were going to work on the part that combines everything together. And the silly thing that I was going to do was, and I think I'm still planning on doing, is to actually just go ahead and change all the numbers to the lowest number. All the numbers in a set, so all the parts of one set, when I'm combining it with another set, to change all the nodes, all the subsets, to be the same node, to be the smallest number in both sets. So let's just go ahead and, I guess, do that. Okay, so basically in list 1 we're going to be checking, let's say, to the right, and then for list 2 we're going to use that one to check down. So when our code reaches here, we've selected a random number, and then we remove it. And right here is where we've selected it. So this is where we display this right here. It says, hey, we've selected this particular number. And since it's the list 1 one, and the code that we're going to put here is to move to the, we're going to see if we can connect it to the right. So so how do we do that? So I guess we need to convert the first thing we need to do is convert whatever our number is, whatever R means, from 1 to 30, from 1 to 32, or 0 to 31. We need to convert that to a actually is it B? I'm sorry, list 1 of R, right? Because R is the index. We need to convert that number to a two-dimensional coordinate, so a two-dimensional number. So if it's, so we probably need to divide it by 16 or something, or divide it by 8. to see where we are vertically. Let me go ahead and I'm going to find a pen and yeah, we'll go ahead and draw this out. So I got our sheet right here, the one we were working on with the maze. And here's our, well, actually this is the part that we're interested in, 1 through 32. So if there's 32 and we have 8 going across, then this should be number 8 right here, and then this should be number 9. So given this number, you know, the value, we need to get our x, so this goes 1 through 8, and this goes 1 through 4. That's our y. So if we divide this number, whatever it may be, by 4, that should give us our y value. Or if we divide it by 8, sorry, it should give us our y value. And then if we subtract that value times 8, the non-fractional part of it, the integer part of that, and then get the leftover, the remainder, that'll give us our x value. So that seems to be the right way to go about this. But we don't want to do that twice. We just want to do it once. Because here we're saying we want to, well, we have 2 lists and we're selecting a different random number, so I might have to do duplicate code unless we do some kind of function, which is really obnoxiously difficult with the TI calculator. So let's just go ahead and just write it for list 1 for now, just to get the code there, and then we'll decide how whether we're gonna copy it or not. So let's just go ahead and store that. Our list 1R, we're gonna store that into what variables have we not used yet? Because I think we're using B. Might as well just go with C then, I guess. So we'll just use C, and we'll say C divided by 4 gives us D. I don't know if we've used D or E, so I'll just have to double check, I guess. Let's take the integer part of that. So that'll give us, no, I'm sorry, C divided by 8. That should give us D, and then D plus 1 is going to be our y value, because that's going to give us 0 through 3. Oh, this isn't good. So if C is, we might have to just subtract 1 from C, because we want 0 through 31, because 32 divided by 8 is going to be different than 31 divided by 8. That's going to be 4 instead of 3. So we're going to subtract 1, and then we're going to add 1 to that number, and that will give us, that should give us our correct y value. That should give us 1 through 4 if for the ranges 1 through 8 and so on. and then we take the extra amount of that, so d times, I guess d minus 1 times 8 and we should subtract that from the original number. So for example, if it's 32, if c is 32, then d minus 1 will give us 0 through 3, depending on what it is, and then we'll multiply that by 8. So if it's, so we never just subtract 4 from it. We're just subtracting 0 through 3 times 8. So we're either subtracting 0, or subtracting 8, or 16, or 24 to give us what row we're starting at. And then the leftover is going to give us our x value, so it's going to be either 1 through 8. So for example, 32 minus 24, that's going to give us 8. That's like the bottom right corner. But if our x value is 1, then, well, 24 should be right at the end of our second row. 25 should be the next value, should be the start of the bottom row. So 25 minus 24 is 1. So that should give us our x value right there. So right now d and e are pretty much our x and y values when it comes to 1 through 4 or when it just comes to a 4 by 8 matrix. Not sure what the best route to go here is. Do we? I don't know if we have a matrix that's it's 4 by 8, do we? We do. Matrix A, but have we used it yet is the thing. If we've used Anyway, did I have a pause at the bottom of this? Okay, I might add a pause just to make sure that this works correctly, because I want to check. Once we combine two sections, like two sets together, I want to like display it. I want to show it so that we can see, you know, what's going on, just to make sure, because it's really hard to debug this otherwise. It's really hard to make sure that everything's working properly. So that should be our D and E. Okay, I got an idea. I got an idea just for now, and that it'll just check the code. It'll check the code that we've just made, just to make sure that that works. Okay, so here we go. Okay, so it says 32. I think 32. What was 32? That's the number. What is 32? I'm not sure why it says 32. Anyway, 20 is the number that we selected. And it says 3 and 4. So using this map, if we were to look where 20 is supposed to be, it should be in the third row. Because this would be 16, 17, 18, 19, 20. So it'd be the fourth one on the third row. And you know what? It says third row, fourth one. So it looks like my math was correct. Looks like this will work. But the algorithm is not done yet. So even though that works, we're still not done with combining sets. So let's just go back down here again and check this. So here we go. This appears to work, so I'm just gonna, well, I guess I can leave that in there for now. So here we want to we can kind of ignore, well, all of these 5 lines right here, those are fixing this, those are just resetting the list, so we, doesn't matter if their code comes before or after that, as long as we don't screw up the variables there. If we wanted to screw up those variables, we'd have to obviously write this underneath of it, but I don't think we need to use the variable r. So let's go ahead and check which one is lower of the 2 sets that we're combining, which is, in this case, since we're moving right, it would be our current coordinates, and then depending if we're wrapping the screen or not, it would be all the way on the left, or it would be just the one to our right. So our first number is going to be matrix A, D, comma, E. I don't know what variables to use, so I'll just use F. And then since we're going to the right, I'm going to say if E plus 1, or if E, I don't know, if E equals 8, I guess, because that's how wide it is, right? No, 4. Wait, no, it's 8. Sorry. If E equals 8, then let's say 0 stores E, and then what we'll do is we'll say E plus 1 stores E, and then we'll just use the same, I guess, variables and just stores them as the next variable. So what we're doing is we're selecting whatever spot we just chose in the square, and we look to the right of it by incrementing E, but if E is 8, we want to start over at the left side again, so we just set it to 0 before we increment it. So it'll be 1. So now we have F and G. F and G are the 2 numbers that we need to check which one's lower, and then we need to check the entire matrix, and we need to set all of the numbers of either of the other one to be the lower number. So basically we're going to assume that we're going to have 2 cases, so either F is already less than G or G is less than F. If G is less than F, then we're going to switch them. So if G actually there's 3 cases. If G equals F, then we don't need to do anything at all. So first of all, we're going to just make sure that they're different. Okay? And then if that's true, then we're going to check if G is less than F, and then we're going to do something there, and we're going to swap them, actually. So this is going to take 3 lines, and we're going to do something after this. So, okay, so if G is less than F, then we just want to store, I guess, F into T, G into F, and then T into G. Now they're swapped. Okay, so now we have 2 numbers, and the smaller number is F, and the bigger number is G. Okay, that's what's guaranteed in this little spot of code here. So now what we need to do is we need to make a for loop. And to be accurate, we actually need to make 2 for loops. I don't even know what variables I can use anymore. Let's see here. So we're I really don't know what variables we can use here. It looks like we might be able to use x and y actually, which is kind of silly. Yeah, I do not like not being able to tell which variables I'm using. It's really getting confusing. So for y is 1 to 4, x is 1 to 8. If matrix A of y x equals G, okay, then we're going to store f into that spot. So basically we're just setting them all, and I think I'm doing this. I never programmed this before, by the way. I've never made this disjoint set data structure, so it's almost kind of strange doing this. Okay, so we have a pause, and then we have like this loop thing. So this is what I want to do. So if we're going to do, like, if we're going to go through looping through and setting everything, I want to do something here just to watch what's happening. So I'm going to display matrix A, and then I'm going to pause. That's a control, isn't it? Okay, and then after this loop right here, same exact thing. I'm gonna pause after displaying matrix A. So let's go ahead and run it again. So there we have 1 and 7. Press enter, it shows us the matrix. Nothing's changed. Now it needs to combine 1 7 with its neighbor, whatever that is. And it looks like we have invalid dimensions, which means we probably set our, well, y and x apparently are the wrong size. I'm not sure why. Y is 1, x is 1. How is that possible? That's got me confused. I'm not sure why. I'm not sure why this would be wrong. We were down here, weren't we? It did crash here? Oh, maybe, okay, maybe, I think I know what happened. I think it resolved x equals g, and it said, oh, you know, that's false, so it returned to 0, and so it tried to access 1, 0 instead of yx, or 1, 1. So let's just try that again. That's probably what was happening. Here we go. Enter. Enter. Here's our matrix. Trying to swap 2, 1. So that should be that 8 right there with the 9. Yes! Look at that. It converted both of them to 8s. So it properly combined the sets right there. So let's see 3, 3. So where's 3, 3? 3, 3 should be this one, and so it should combine with that 19 should turn into an 18, hopefully, if it works. It did. So if we keep doing this, if it works correctly, all the numbers in the entire thing should be 0 at the end. So we should just keep going through, and eventually everything will turn into the number 0. That's supposedly what would happen. So let's just see if it let's see what happens. We could take out, I could go back and take out all the pauses. Actually, what's going to happen is, sorry, it's not going to turn 0 since we're not doing it vertically yet. But what's going to happen right now is hold on, let me think for a second. If we're moving to the right, why do we have... Oh, right. We're using matrix A. So we actually need to use both lists if we're going to combine everything to be 0. So what should happen is the first row should turn into 0s, the second row into 8s, the third row into 16s, and the fourth row into 24s. It won't turn the entire matrix into 0s yet. It's just going to turn it into 0, 8s, 16s, and 24s. That's all that's going to happen. But if that does happen, then that means we've done we haven't made any bugging, we haven't made any errors yet. So everything's looking good so far. Nothing seems to be straying out of pattern. Nothing seems to be turning into numbers that it shouldn't turn into. There we go. 0, 8s, 16s, and any time now it should be 24s. Zero, 8s, 16s, 24s, and I think we're good. Hopefully it doesn't like try to crash or anything when we finish. Hopefully it just peacefully kind of finishes the loop, which it should. Come on. There's a lot of... Oh. There's no way to check if that finished correctly because we just restarted the program. But it looked like it was heading in the right direction towards the end there, so... if it finished, we already knew that the lists finished correctly before, so I think... At least it looked like they did when we worked on it. Anyway, let's go back. Didn't take out all the pauses, so but let's just combine the vertical ones now. Let's not worry about just doing it horizontally. So here we go. Right. Let's do this. Okay, so list 2. Okay, so I have to kind of memorize what I did here. Because it's a lot. So, wow. Whew. Okay, so wow. Okay. So we figure out C. Okay, so we store it as C, and then we figure out D and E. That's the first thing we need to do. That's the first thing we need to do. Okay. Where is that? Here we go. Okay, so here we go. We have L2, R, we store that as C, and then we display this as C here. And then we got to figure out D and E. Wow, I almost can't even remember how I figured out D and E. So if we have the first row, so its number is 1 through 32, so we need to take c minus 1 is what we're interested in. And we need to, I guess, divide that by 8 and take the integer of that, which means the non-fractional part. That's what int does, by the way. So c minus 1, that'll give us 0 through 31, and we want to divide that by 8, and that'll give us 0 through 3, and then we just add 1, and that should give us d. And then d times 8 will give us 8 through 32, so we need to subtract 1 from d to get our interesting value here. Okay, and then we want to subtract that from c, and that will give us, that should give us e. Did I do that right? I think I did that right. And then I guess it doesn't really matter too much, but we can pause it there. We can then here what we needed to do, I guess, a couple loops to go through and make sure that one of them, I guess we need to get the indices or we need to get f and g, that's what it was. Okay, so matrix A of DE, right? Because D is the Y value, right? Yeah. Okay, so matrix A of DE we're going to store into F, and then we're going to increment E, but we need to check if E is 4 this time, not 8, because we're checking downwards. So if E equals 4, sorry, then 0 stores E, and then we're going to increment it, and then we're going to get G. Okay, and then now that we're here, we have both values. Now we need to loop through, and we need to well, first we need to swap them if one of them is larger. But what we're going to do that is we're going to branch to do that. So we're first going to check to see if they're different, like we did before, because it's kind of duplicate code, which is actually not a very good computer science thing. But this is, might I remind you, a slightly primitive language. It's not like, functional like Haskell or something where we can just make this function and pass it in. It doesn't really work like that here. So, and it's also, I guess, simpler to kind of implement as far as like as far as simplicity with technology and just our understanding. Anyway, point is, we have to rewrite this code just because it's easier to do it that way in this case. So if G does not equal F, right? Then we're going to do something interesting. Otherwise we just kind of skip it and let it be removed from the list, that particular iteration. So now we see if G is less than F, then we swap them. So F stores T, G stores F, T stores G. Okay, and then now in this piece of code, just like before, f is smaller. So since f is smaller, we need to loop through both. Wow, this program is getting pretty long already. Okay, and then there's two lines in here. There's an if branch in here actually. Or no, wait. Is there an if? Yes, there is an if, sorry. If we're going to use y and x to go through the matrix, and we're going to see, and we have to close that, and we're going to see if that is equal to the larger number g, then we're going to store f into it. And I lied. What did I lie about? Y, I lied. Here, I'm stupid. E is our x value, right? So we don't check if that's 4, we check if d is 4. So unless we swapped these, that doesn't make any sense. So if d equals 4, 0 stores d, and then d plus 1 stores d. So that increments downwards. That's what we're doing. Okay, so y is 1 to 4, x is 1 to 8. Yes. We are almost done. Let's see if that works. Okay. Okay, we got an L2, so at 2, 2, we got to see if the matrix combine. Oh, you know what? Hold on. I didn't print it, but maybe we can look. See if 2, 2 combined with the 1 under it. Okay, so it did. So here's 9, and it combined with 17. So it looks like that particular iteration worked. So there's a good chance the whole thing works. Cool. So I think we just might have a functioning set data structure. So okay, so we're done with. I think we're pretty much done with phase 2. So let's. I know what we have to do to finish this, and that's to make our final data structure, which is going to be the walls. That's kind of our final output. And so we'll just go ahead and we might be able to finish the walls, but I'm not sure if I should end the episode and give us as much time as we want to work with the walls, or if I should just kind of finish it during this episode. But I don't want episodes to get too long. So we might just have more fun, because there is a lot of GUI stuff that we might want to do with the walls and things like that. So we might have to spend a lot of time even picking just our variables and things like that. So I might have to decide on just ending the episode. Even though we're close to getting something working, I want to learn how to end the episodes at the right times. So we did get the wall, we did get it working, I believe. The way that I want to check this is I'm going to go up here and I'm going to delete all the all the pauses. So these displays, okay, display C, display M, display L2. I just want to get rid of these because it's, I think we should be able to debug without them now, because we've seen that even when we have them, everything works. Okay, display C, display L1, display L. Okay, so if we run maze, what should happen is it should just kind of execute for a while, and you can see that in the upper right hand corner. We're not going to really see anything until it's done. But I think it's just processing the entire thing now, and if it works, then what we'll end up with is our matrix A will just be all zeros. That's what we'll see. And what that means is, okay, so why does it take forever to make all zeros? Well, that's not the end goal, but that sets up the skeleton algorithm for generating the actual walls. So if we do have all zeros, then that means we properly, yep, all zeros. Okay, so that means that all the rooms, if in case you don't understand what this means, is it means that we've marked every room here why is this 30? Wait, hold on. I'm confused. What? Why do I always use 32? I specifically programmed this to work. Hold on. I think we've combined. So hold on a second. I'm kind of confused about something really for the moment, and that is why. Okay, so there we instantiate. Here we instantiate the. We instantiate A, and 0 is the upper left, and then 31, I believe, is the bottom right one. Okay, that's why. Okay, so basically, I actually did something silly here, and that is... okay, so the silly thing that I kind of did here was, okay, so the same matrix is kind of represented by two different things that it's kind of my fault that it did this. But anyway, in one case, and when I say 1 through 32, the reason that is because these lists here represent, they use the numbers 1 through 32 to represent every item in the matrix. But the item values themselves that are stored in this matrix, not the index of them, but the actual values that we're storing to keep track of whether we've combined the sets, that's not 1 through 32, that's 0 through 31. But it's okay that it's different. It still works because they're not the same thing. They're actually, they're being represented at different levels here. So, yeah, the 1 through 32 is more of an index relating to the lists, and then the 0 through 31 is sort of, it still is kind of similar to an index, but we're not using it to actually index the matrix. What we're using it for is we just decided to use those particular numbers to represent this, to identify our sets. And so just 0 through 31 just happened to work pretty well. That's the only reason. And it's good to know the difference between those two, because I don't want to get my sets confused with my list index, because they're two different things. They don't have to be the same numbers. They can be other crazy numbers. Especially the sets one. The sets one we could have just picked 1,000 through 1,031. It doesn't really matter. So as long as the smallest one, as long as you can compare them, is what matters for that one. And so there we go. That should be about it for that episode. I will probably make another episode soon. I just want to quit while I'm ahead and be ready to spend an episode just having fun, possibly generating mazes, and maybe we'll get to explore a maze or two. And we have yet to make them expandable. So far our mazes are just one screen size. And you know what? I was thinking maybe we should implement this with Zelda and combine it with our Zelda game, and then we'll have mazes in our Zelda game, because this is very this is very similar, so who knows? We might just have some fun with that. Anyway, this has been Tim, Calculator Programming with Tim, and I'm out. I'll see you guys later in the next episode. Goodbye.